Alright, in 6.3 we're going to do some solving equations of multiple trigonometric functions and arguments. The one thing we have to keep in mind too is on these problems, guys, we are still going to have an interval. So we are only going from 0 to 2 pi. So keep that in mind when we have our solutions and where that ends up. So, example 1, solve the equation 3 sine cubed equals sine squared. So what we want to do first is get everything to one side. So I'm going to subtract sine squared x from both sides. And that equals 0. Now I see that they have in common, they have a sine squared x in common. So I am going to factor that out. That's sine squared x times 3 sine x minus 1. That allows me to have both parts that equal to 0. So on sine squared x equals 0, when I solve for this, well, that's the square root, so sine x equals 0. I know that sine x equals 0 when x is pi times k. Now I also know that since we are only going between a 0 and 2 pi, that k in this situation can only be 0 and 1 because it's not including the 2 pi. So if I put in 0 in there, I get x equals 0. And if I put 1 in for k, I get pi. Now I need to solve the other side. So I get 3 sine x minus 1 equals 0. Now when I rearrange this, I'm ending up with sine x equals 1/3. Well, 1/3 is not on our unit circle, or I shouldn't say it's not on our unit circle, but it's not one of our nice numbers, which means to solve for x, I'm going to have to do the arc sine of 1/3, and then of course that's 2 pi k. Now of course there's another value up there, right? And it's going to be pi minus arc sine 1/3 plus 2 pi. We proved this the other day, and I think it was 6.1 and 6.2. Now, think of our case. Well, in this case, k can only be the value of 0. Okay, otherwise we're going beyond 2 pi. So, that means that x equals, well, if I plug in 0 for k, I get arc sine of 1/3. And for the other one, I get pi minus arc sine of 1/3. So I have 4 answers, or 4 solutions. Okay, example 2. Well, in example 2, we want to actually think of our trig identities that allow us to solve better. So I'm going to switch the secant squared to 1 plus tangent squared. Now my next step would be to move everything to one side, and I'm also going to arrange it in order. So I would end up with tangent squared x minus tangent x minus 2. Now, if you guys think about this, this is a quadratic, so we can actually factor this into two binomials. When we do that, we get tangent x minus 2 times tangent x plus 1. If you need to think of this as u squared minus u minus 2, and then factor that. Okay, guys, what two numbers? So on and so forth. This would be u minus 2 times u plus 2 plus 1. And then u is actually my tangent. Okay, now we have these two parts that we can set equal to 0 separately. So I get tangent x minus 2 equals 0. And I'll solve for that. So we get tangent x equals 2. Alright, so that's not a nice number on our unit circle. So we get x equals arc tangent of 2. And we know this happens every pi k. So in this situation, k can be 0 or 1, and we're still in our interval. So if I put in 0, I get x equals arc tangent 2 and arc tangent 2 plus pi. Okay, that's one part. Let's do the other one. Tangent x plus 1 equals 0. Tangent x equals negative 1. Well, we actually have a negative 1, right? So that means x equals negative pi fourths plus pi over k. I think it's in the fourth quadrant, and that would be a negative pi over 4, right? Going from the x-axis there. And then we're doing that every pi. So again, I can put in 0 and 1. So if I plug in 0, I get x equals 3 pi over 4 and 7 pi over 4. And yes, guys, you could have thought that as, hey, I know that this is in my second and fourth quadrant, and I'm only going around the unit circle once, so 3 pi over 4 and 7 pi over 4. You could think of it that way also. Alright, example 3. What I want you guys to keep in mind is that we are still dealing with the interval 0 to 2 pi, even though it wasn't written down on there. So let's do this. What we need to do is change this double angle. So what's really going to help us, because cosine 2x has 3 different things they can use. Well, let's keep with the tradition like we did in the last example of doing those factor into 2 binomials. So we would need this to be cosine squared. So I'm going to use the one with cosine squared, which is 2 cosine squared x minus 1 equals 3 cosine x minus 2. Move everything to one side. I get 2 cosine squared x minus 3 cosine x plus 1 equals 0. We're going to factor this again. If you need to think about it, think of it as 2u squared minus 3u plus 1, and factor that out. When we factor, we get 2 cosine x minus 1 times cosine x minus 1. separate these two. So I get 2 cosine x minus 1 equals 0. Solve for that, I get cosine x equals 1/2. Well, we know that this happens at pi over 3, which keeps going around and around and around. And we know it happens at 5 pi over 3. And that keeps going around and around and around. But the only k that works in our interval is k equals 0. So I get x equals pi over 3 and 5 pi over 3. Now that was only for one part, so we still have to do the other. We get cosine x minus 1 equals 0. And we get cosine x equals 1. So where does it equal 1? Well, cosine, that's x equals every 2 pi k. And the only k that works in this position is k equals 0, which makes our x equal 0. So we only have 3 solutions in this case. Example 4, there was a misprint, so we're just not going to do it. There's a lot of examples that we can deal with above. Example 5, though, we will do. So, in example 5, we need to change this double angle. And we're going to change it to 2 sine x cosine x equals the square root of 3 cosine x. Let's move everything to one side. So we get 2 sine x cosine x minus square root of 3 cosine x. Now, because we have 2 different trig functions here, I'm hoping that we can factor something out. So, here they both have in common a cosine, so I'm going to factor that out, leaving us with 2 sine x minus square root of 3 in parentheses. I will separate those two, so cosine x equals 0. Well, that is at every pi over 2 plus pi k. In this case, k can be 0 and k can be 1. So we get x equals pi over 2 and 3 pi over 2. Where on this side we get 2 sine x minus the square root of 3 equals 0. When we get our trig function alone, we get sine x equals square root of 3 over 2. Well, this is nice because these are all on the unit circle. So we get x, this happens at pi over 3 and every 2 pi k. And it happens at every 2 pi thirds every 2 pi k. But of course in this case we can only get k equals 0 here, otherwise we'd be out of our interval. So x equals pi over 3 and 2 pi over 3. Alright, example 6 we're actually not going to do either, so cross that out. Just keep in mind that when we're solving, think of your factoring, think of moving things over. Also, I understand that we're just dealing with once around the unit circle, but because not all of our solutions are very nice numbers on our unit circle, you want to keep in mind every solution and then ask what k's make it so it stays within the boundary.